Hey, hello, good morning. You my heroes. Honestly, like first talk, second day of the conference, you didn't go to the party yesterday, did you? Yeah, right, that's what I thought. Well, I'm glad you're here. I hope to wake you up with a talk about AI and Java. But before we start, raise your hand if you've done anything AI with Java. Are you my crowd? OK, cool. So just to be clear, this talk is very basic. We're just scratching the surface, and this talk ends where most exciting AI talks begin. Right? So we just go a step back and look into the very basics of integrating AI solutions into the Java world. My name is Milen Dyankov. I work for a company called Pinecone. I'm a developer advocate. I've been a developer, much like most of you are, for pretty much the entire my career, which is close to 30 years now. But what's most important is who am I not? I'm none of these guys. I'm not an AI expert. I'm not a machine learning expert. I'm not a data scientist. You know, all these smart folks that do like math that you can barely fit in your head, I'm none of those folks. Right? But I've built software for 30 years, and I do know a thing or two about how to build enterprise software. And now that the AI is here to stay, and it's going to enter that land, I was on a journey to explore how that actually fits into our applications and start with what the heck is AI. So we're not talking about this today, super intelligence. No, you're not going to be able to build the Terminator on your way out. Like, if you have these expectations, forget it. We're not talking about general intelligence either, which Sam Altman would really like to see tomorrow. I have my doubts about it, but we're not going to be talking about that as well. We'll touch base on what is known as artificial narrow intelligence, which is basically some sort of software that's intelligent enough to not know how many fingers are in the hand. So every time I say AI in this talk, keep in mind we're talking about this narrow intelligence that is the most widespread in the world today. Why this talk? So some time ago, I was like, OK, this AI thinks like everywhere. Everyone's doing it. But what is it? Like, I'm a Java developer. What I need to know, like how to interact with that thing from my Java code. OK, I get it. OpenAI has an API. It's just an API call away, right? But that's, as a software architect, someone who designs systems, that's by far not enough for me. So what I needed was a mental model of like, how are the things in that new world? How is one connecting with the other? What's the interaction point, and all the things that go around that. So this talk is about that. It's going to give you, hopefully, a mental model of the things around us on a very basic foundation level. And as every model, it's going to be wrong. Now, keep that in mind during the talk, because especially if there are some experts in the field, many times you would be like, well, what he's saying is wrong. Yes, I'm aware. And to explain to you why it is wrong, I want you to give a look at that map. So that map is wrong. And the reason it's wrong is because it looks like Greenland and Australia are the same size on the map, whereas if in reality, their size is significantly different. So the map is clearly wrong, but it's useful. It tells you what's where. It tells you how to get from one point to the other. It tells you there's an ocean you cannot easily cross and things like that. So the fact that the map is not as accurate as you would assume looking into it does not make it any less useful. So will be the context of this talk. A lot of things I'm going to tell you today will not be very accurate from purely mathematical and scientific and data science point of view, but they will help you, hopefully, build a map of what is where and how to work with this. And so when I started working with AI, the word that you hear the most is models. Models here, models there, models everywhere. And wait a minute, what is a model then? So that was like my natural first question to ask. Just one sec, sorry. By the way, I don't see the clock on the screen down here, so if you can make that work, thanks. So what is a model? Now, start digging into it. The model in the AI terms is something that everyone's using. On one side, you have the very smart folks, the data engineers, scientists, who are using data to train that model. Whatever that model is, they somehow train it and produce an artifact called model. On the other hand, are we developers doing what's known as inference. Like, we are interacting with that model, asking it questions, asking it to generate something, asking it to fix some whatever, which is users of that model. OK, so but what is the model then? I start digging into that. There's tons of documentation, articles, whatnot. And if you understand Python and want to read, play around with notebooks in Python and whatnot, there's like tons of resources out there. How is that any useful outside the Python world was my question. And so I started digging into that. And one of the first definitions of a model I found was it's a function. Right? It's a function, it gets some data, and it transforms it to some other data. It's like, and mathematicians are totally fine with that definition, by the way. Like, you give them this, and they're, oh, yeah, I understand. It's like, what do you understand from this? But yeah, it didn't work for me. Maybe I'm just not smart enough for this. But I'm thinking then in terms of developers. Like, maybe it's some sort of a method or function in terms of programming language, that you have the output and the input, and it kind of somehow out to generate the logic. Like, that was my initial way of thinking about it. But then how you generate that logic just didn't click either to me. And then it clicked. Like, when you use something like model, like in terms of what we use like ChatGPT and similar, it's kind of interacting like the kind of same sort of interaction we have with a database, right? If you think about it, there is something that has some knowledge, some data, and you ask it a query. You say, give me this, produce this, calculate this, whatever, and gives you a result. Now, the difference is you don't have to use a structured language to talk to that thing, like SQL or whatever the NoSQL language is for the given thing, but it's conceptually the same thing. You have a piece of something that has some information, and you query it, you get some information back, or you ask it to produce something out of that information. So this is where it clicked with me, and I was like, oh, OK, let me see, what would I do as a developer if I didn't have AI and I had to invent it myself? I know enough about databases. I assume you also do a fair share of database work. So you're probably not at the level where you would build a database yourself from scratch, but you surely know how to use one, I hope. And so here is the demo that I put together to kind of demonstrate this, and based on my early experience. So this is a UI for my database. This is Postgres. As you can see, I have no tables, no nothing. I do have a CSV file which contains information about books, basically titles and descriptions. And what I'm going to do now is I'm going to import that file into the database. You don't have to pay too much attention on the SQL queries. It doesn't really matter. What it does is it creates a table with a bunch of fields, which we're not going to need. We're only going to help focus on title and description. And it then imports the data from the CSV file. And it creates an extension to the database. Uh-oh. Laser pointer, not really good at this. But the last line, 18, it creates an extension vector, which is a Postgres extension that allows you to deal with vectors, which we'll be using later on. That's the entire thing. So now, if you go and check, you'll see that we have a table books. And if we open that table, you will see that we have some books in there. They have some titles, and they have some description, and they have like lots of other things, which again, we're not going to be using for this presentation. So what we want to do now is to query that database that we have for specific things. All right, so here is what exactly we want to do is like the commented lines out there. So I ideally want to say, give me all the books about animals in the rainforest, or all the books that teach me how to play a song on a piano. But I cannot do that with a database that easily, right? What I can do instead is what I'm doing now is select from the table where the description contains something about music, right? But that's not what I really want to know. That's the limitation of the database. If I want to specify more precisely and say, give me something where the description contains piano and contains play, it finds no book at all. So this is where we are limited with like dealing with purely structured data when we want to do unstructured requests. But what we can do is we can use something that popped up in Postgres some time ago. It's called, and it's been very popular over the years, which is full text search. Now, with full text search, we get one step closer. Right, what you see up there, it's the TS vector that basically gets a text and converts it to a text vector. Now, what you see in the results here, the text vector is basically tokenizing the query. So we get the description field of every book. We tokenize it, or it tokenizes it, and it assigns a value to it and say actual equals 91, America 16, analog 195, and whatnot. So it converts a text into tokens and applies like indexes to them how to easily find them. So then you can do queries like the second one, where you can use the toHeadline, which is going to highlight the actual thing that find, and it shows you the rank. And now what we do here is convert the description field to tokens and convert our query to tokens. And we say, find me something where the tokens converted from the description field matches the token in my query. So I'm not doing string matching word to word, but I'm like finding tokens. This helps out with when you have different variations of the word and things like that. So it's pure tokenization thing and finding the token. And you can see the result. It even highlights like where it finds the piano in the description and whatnot. And this gives us like a step forward, but still not like what we would consider AI. There is one more thing that we could do here is we can actually create a table. So we don't do this on the fly. We don't do that conversion every time. We can just create a table, create a column in that table that contains the values already converted into tokens. And then when you select, you will see there is a column which for each entry has this token. So now we can do interesting things like do the same thing basically, but searching from the table itself, right? Without doing the conversion every time we request the data. So tokenization seems to be an interesting approach. So how about we go a step further and we say, there are three things I'm interested in. Whether it's about animals, whether it's about science, and whether it's about music. Like I have books about all kinds of things, but those are my concerns. So what if I was able to figure out somehow whether that book is for one of those topics and assign a value, percentage if you will, like what's the probability of that book being about that topic, right? And then I can do this for all the books. Right, and I can assign like there's a 13 or 0.1349% chance that a given book is about animals and so forth. Right? How do we do that? Okay, so first of all, let's create a dedicated table for this. And you'll see here we create a table called books vector. And it's going to have a column called embeddings. That's what normally those things are called, where we store vectors, which is of the size of 3, because that's the 3 things we want to care about, like whether it's about this, that, or that. Right? And so we created a new table, and the column, obviously, by copying the existing one. And the embeddings, of course, is empty at this point. Now, here is some Java code which will fill up this column. So what you see, the first is the select, basically saying, give me the data from the existing columns, convert TS vector to array, so basically extracts the tokens, not the weights, right? And the second one is an update statement which says, because we do it in a loop later on, so for each record we find, convert this to these tokens, to these embeddings, and put them in that column. Now, the way we convert this is using a thing called naive embeddings. You cannot point it, but it's line 28, if you see the lines. Now, what is that naive embeddings thing? So, naive embeddings is a class that I wrote that's very complicated. Basically a static map. And it basically says, if something contains that word, the probability it is about that topic is that %. So if it contains the word computer, it's 0.9% chance it's about science and things like that. Right, and so we run this code now, and you see it updates the database. So if you go back here and look at the same table again, what you will see is that we now have some values in the embeddings column. So there is somewhere, like record 36 has 0.3% chance of being about music or whatever. OK, good. We have some embeddings in a database. What does that mean? What can we do with that? Now, we can represent those 3 things as vectors. And because there are only 3, we can use a 3-dimensional space, right? Which is nice because it's easy to visualize in a presentation like this. So picture those being the nodes of every record, right? So here is like one, the other, and the 3 dimensions are the numbers that we have in those vectors. Now, if we have a query, we want to know something, we can do the same thing. We can convert it to those 3 numbers, right? It's going to give us another vector, right? And when it gives us another vector, what we can do is we can find the distance between our query vector and the vectors that are already in the database. And theoretically, the shortest distance between us and the vectors are the vectors that have the shortest distance between our vector and themselves are the ones we're looking for, right? So there are different ways to calculate the distance. This, what you see here, is Euclidean distance. There's a cosine, there is dot product. You can go deeper into that. But that's basically what it is, finding how far vectors are from each other. So here is the code that does exactly that. So we select, again, from vectors to arrays to convert our query, which is I want to learn how to play a song on a piano, into a vector set. And then here, OK. And then we have our select statement. So now select statement, as you can see, has no where. So we don't do exact matches here. We basically do order by distance, where distance is defined as the distance between an existing embedding, and that's line 35, and whatever we created as a vector from our query. So basically, execution at line 43, it basically tells you replace that with our search vector, and find the distance. That arrow sign, like less, dash, greater than, thing is equivalent distance. OK, so and that's it. Basically, we just find, and we're limited to the 5 results, right? So when we run this, what you will see is we get exactly that. We get 5 vectors, 5 results of books that are technically the closest one to the one we're looking for. You will see that this is not really, like if I were to say, hey, here's my AI and give it to you, you won't be happy with that result, right? So, OK, but that's the first step. Like, what we can do then? Well, we can say, wait a minute, I don't really want to define what those columns mean. It's nice because it's always nice when we humans understand what's the meaning behind the value, right? But if you want to do this for hundreds or thousands or hundreds of thousands of values, that's impractical for humans. So let's just replace those with some P1, P2, P3, Pn, like whatever dimension we have in mind, and then assign weights. Like we basically do the same thing as with the 3-dimensional space, except this time the columns have no particular meaning for us humans, right? They just mean something. They mean the book is about something, we don't know what, right? And so we can do the same for all the books, right? And repeat the process. There's one problem, though. How do we know the weights, right? And so this is where the entire machine learning discipline and the whole AI thing comes to play. If you have big enough database of data, think internet, what you can do is you can grab this data and train an algorithm to find similarities. You can give it, let's say, let's simplify this to description of books. You can give it some description, say, calculate what is how close are these to each other, then to that other thing, that to that other thing. And it, over time, is going to iterate about and then figure out, like, oh, in one way that it knows what that way is, those things are similar. So let me put that in P1. And put some weights in there. And then in another, it will put them in P2. So it will figure out all sorts of relationships between those documents. You will never know what it is. You won't be able to debug it and see, oh, P67, that is about. No, you're not going to know that. But it will create that table for you. And that's the entire training of models happening. That's why you have, like, and depends on how many of those parameters you have, how bigger, what's the accuracy of the value that you put in. Those models are like larger, smaller, bigger, better, worse, and whatnot. That's the entire training process. And what is the result of this process in this particular case is what's known as embedding models. So those are very, comparing to all the others, relatively simple types of models, which the only goal of which is to convert some data into vectors, into embeddings, right? That's what we did with manually just some time ago. Right. There's plenty of embedding models out there available as proprietary ones, but also many open source ones. You go to Hugging Face, it's full of them. And so how our models are distributed? That's the next tricky question. And not only embedding models, but pretty much all models, because the other models we'll be showing later are very similar in a sense that they're distributed in a very similar way. They're more complicated, more complex, and do other things. But fundamentally, they're all models, and they're distributed in many different ways. Depends on how they were trained, depends who trained them, and whatnot. This is just a very short list of options that you have. So like PyTorch will generate those torch or PT files or whatnot. TensorFlow has their own, and you can see like a bunch of others. Onyx is an interesting one because it's at the time I was investigating this, it was the distribution approach that was supposed to be the universal. Now, you know how the things goes with the universal things, right? You have one more model, or one more way of doing things. But it seems to be popular, and this is what we're going to be using in this demo. So how do you use it in Java? Well, luckily, there is a framework called LangChain4j. And luckily, these folks created something smart to help people who just start with this, meaning they put all these models into jar files. So what's happening is they get this all mini LM, L6, V2, whatever model, and they put it in a jar file. And so what you can do is you can just add that jar file on your class path, and then the Java is going to load LangChain, which in turn is going to load the Onyx runtime, which knows how to get that model from the jar file and run it and use it. And this is exactly what we'll see now happening here. But for this to work, let's just create yet another table here so we have a clean space to work with. You will see the code is almost the same, except we don't define the space for the vector column. We don't limit it to 3 this time. We just say whatever vectors length you want to put in there, put it in there. That's probably not the best practice if you do production systems. You probably want to know what your model size is and limit the size of that column to that particular size, but it works. So yeah, same thing. We have the embeddings column empty, and then we have some code here, which is basically doing the same thing as we saw in the previous example. The difference is it now uses a thing called model embeddings, line 24, instead of my naive embeddings, things that I created myself. Now, but what is model embeddings? Well, it's just, again, something that I created myself, and it's basically has some calls to this jar file, all mini LM embedding model coming from that class coming from that jar file. And if you look into that class, what you will see there is load from jar and the actual Onyx model. Right, so this is what LangChain4j already gives you, is the ability to load this from jar files. Now, this also is a limitation, because to do it this way, you can only do it with the models they already packaged as jar files. Right? If you want to use other models, you're just going to have to follow their approach of loading them from Hugging Face or wherever else you want to load them from. But essentially, that's all it is. It loads the Onyx runtime environment, and it loads that model into that runtime environment, and then you can talk to that model. And that's exactly what we do here. We talk to that model, and we tell it, here is my text converted to embeddings. And when it converts it to embeddings, we put it in the column that we created in the database. And this is like a 1,000-record database, so it's really nothing in machine learning terms. But it's enough to demonstrate. So if we go back to our database and select this is what our embedding column looks like. Tons of numbers. I think the dimension of this model is 300-something vectors, so it's a relatively small model. There are models that use thousands of dimensions of thousands. But for the purpose of what we want to do today, that will be more than enough. So that's what it is. A vector is like a line of number. So now we're doing the same operation, but not in 3-dimensional space, but in 300-something dimensional space, trying to find the vectors that are close to our query. And how do we do that? Well, exactly the same way. We have, as you can see, very much the same query. Find me the vectors that are close and limit them to 5, and that's it. And let's do that now with the actual embeddings that came from that model. Now you can see, I probably don't remember the results from the previous query, but as you can see in here, the books that it found do have something to do with music. Now, they're not going to tell you how to play a song on a piano, but they do. But it recognizes that we are in the context of music and playing, and they have like Chopin, the man and his music, the music in the brain and mind, and whatnot. So the results are much closer to what we're looking for, rather than just our naive implementation of this is about that. OK, so this is what we have currently. But we're still back in the world of databases and using an extension for Postgres. And if you want to do production load, that's probably not what you want to do. Those things are great for small-size things. If you want to go really large size with this, you probably need a embedding store, like a dedicated solution that allows you to store vectors and efficiently search in data sets that go like hundreds of millions or billions of vectors, right? I'll show you one. It's called Pinecone, surprise, surprise. And that's my account there. What you look typically in solutions like this is the place where you store indexes. Like I have 2 indexes here, which are for other projects. And I'm going to use, again, one simple API call here to create a new index, which I'm going to need for this demo. The reason I'm putting AWS and US East 1 here is because that's the region where our free accounts are created. We do have like very generous free plan. So if you want to do that, you probably want to specify AWS and US East 1. And that's it. You run that. And it does the same thing we had before, iterates over everything in the database and creates embeddings. And then instead of storing them back in Postgres, it will upload them into the vector store. And if you look at the vector store again, now I have a new index here, which has 1,016 records. And down below, you will see the first, I believe, 10 or so records. You can see like what we stored there in the metadata. We have the text segment, which is the text that we indexed, and the title. And somewhere in the edit, you will see the dense vectors. I'm not going to go into details what's the difference between dense and sparse, but there's other things you can do with vector databases, which you may want to explore once you reach that point. So now that we have it there, how do we get the data from there? Well, luckily, LangChain4j has also tools to work with embedding databases. So this is like an embedding search request, model embeddings and stuff. Those are from LangChain4j. So basically say embedding store search, embedding search request, and it will do the API call for you and get the results, the 5 results we are asking for. And so let's see that working. Hopefully not. It's going to take a long time. And you see pretty much the same result, except this time it doesn't come from Postgres. It comes from the vector database that we used. OK, here we are. So we talk about embeddings, finding stuff and whatnot. And you probably at this point is like, wait a minute, we were supposed to talk about AI. Like, what this has to do with AI? Well, surprisingly, it has a lot to do on a conceptual level. So what we came to explore was embedding models, and the idea that you can extract meaning from something by comparing it to something else. Right? So you don't know what the meaning is. And if you remember the keynote, there was a very prominent sentence said there that we think this is reasoning, where it is not, it's a prediction. And that's like 100% true. It's not reasoning, it's prediction. The reason it's prediction is because it's trained on how similar is this to that, and this to that, and this to that. And that's the only thing it knows, similarities. Right? And so when you know that, on a large scale, it allows you to do predictions. In a way, like we put stuff like in this column if it is about this. But we can reverse that. We can say, here is my text, and based on what you've been trained on, find me the word or the token or the thing that is closest to what I'm giving you. And it's predictably the next possible word. Right? Then I get that, whatever it gives me, as I do the same again. Give me the next possible word. Do the same again. Give me the next possible word. And in very basic terms, that's how LLMs work. That's the entire generation. It grabs something, finds something similar. Oh, now it's longer. Find something similar. Oh, now it's longer. Find something similar. And it builds up the output. So it builds by similarity, not by reasoning. Now, obviously, things have evolved a lot. And if you talk to machine learning experts and AI experts these days, they will tell you all about how that actually works these days. I'm not going to go into details about that. It's by far more complicated than what I'm explaining. But that's the general concept of LLMs. They just predict what the next thing is. And so we can use a very small LLM to demonstrate that. There is an open source one called Tiny Llama. It has 1.1 billion parameters, and it's meant for chat. Now, how do we use that model? That's different from embedding models. That's a model that you can actually ask it something, and it will give you a response. Well, we can use a library called JLlama. How many of you have heard of JLlama? Yeah, no one. That's what I expect. It's a relatively new library. It makes use of Java's new vector API. So if you want to try it yourself, you're going to have to put some parameters, like use whatever new features in Java. It just doesn't run like out of the box. But it runs once you set up the parameters correctly. So basically, LangChain knows how to work with JLlama. And so we can do the same thing. That's the entire code, believe it or not. So basically, what we have here is the same query. I want to learn to play a song on the piano. And I'm telling LangChain that I want to use a JLlama chat model. So I'm building that model from, and I'm giving it the address of the model. Now, that's a Hugging Face ID. So what's going to happen, I do have that model downloaded already, but if I didn't, it would go to Hugging Face, download it, install it local in my cache, and run it from there. So, and that's it. It's going to figure out what runtime it takes to run this, and we'll be able to run it. And then I can just do model, generate, and then query, and pass some text to that model, and it's going to give me an answer. Let's do that. We're going to click on that triangle icon here, and then we're going to wait. We're going to wait about 73 seconds on my laptop, which I'm not going to make you wait here, obviously. And about 73 seconds later, you'll get this, the response from an LLM. Now, that's a relatively new laptop with equipped to run this thing. So on my previous Intel-based laptop, this thing was running roughly 5 or 6 minutes before it produced any results. So just to give you an idea. But it gives you information how to learn to play a song on a piano. It's a very small model, so don't expect quality of things you get from ChatGPT and stuff, but it's good enough. It has nothing to do with our database, though. It's just random data that it was trained on. So this is where we are. It's slow. So how to make it better? Well, we make it better by at least eliminating the need to run this within the Java runtime. And so what we can do is we can use things like Ollama. How many of you are familiar with Ollama? Okay, a few hands. So Ollama, for those of you who don't know, is a Docker for models, basically. And you can do the same thing here. I want to learn to play a song on a piano. and you tell it which model you want to use. In this case, it's Llama 3.2. And then you create a no-Llama model. You tell it on which address it listens. This is the localhost in my case. So what listens there, though? Now, this is my terminal. And if you just do Llama when you have it installed, you can see it's very similar to Docker. You can do a Llama list. And it's going to tell you what models you have downloaded. So I have 5 models downloaded locally on my computer. And if you do a Llama PS, you will see none of them is running. They just download it and sit there, right? And so that's my entire code. I do the same thing like I did before, except this time I'm not using Java to run the model, but I'm calling Llama, which is running the model. This is going to take a few seconds because, as you saw, the models are not loaded in memory. So the first thing it needs to do is to load the memory, the model in the memory. But once it does, the request is fairly quick. And we get our response from this time from, I think it was Llama 3.2 model. Or something, and it gives us some result. Of course, it still has nothing to do with what we have in our database, but it's a generic response from a generative AI, from a relatively small model. Now, if I go to the command line again, and I do a Llama PS again, what you will see is that it actually started a Llama 3.2 model, and it uses 100% of my GPU. Well, no, it actually means that it runs 100% on the GPU. If you don't have a GPU, that's going to be significantly slower. But yeah, that's basically what we can do with Llama. Now, Llama has own repository of models that you can use through Llama. Right? So it's not any model. It has to be in Llama's repo to be able to use it, but it offers quite a few models, so it's definitely an option, especially if you do POCs and prototyping and stuff like that. And through this entire exercise, we've been using LangChain4j. And what you saw from LangChain4j now so far is that we can call an embedding model to create embeddings from text. Now, we can technically do the same thing for images and video and audio and whatnot. It's just more time-consuming. That's the reason I'm not showing you here. But it's conceptually the same approach. You can even find good enough models that can give you multimodal models. So you can extract meaning from image and extract meaning from text as embeddings. And then you can search and say, find me the image that is about this, right? And it will use the text embedding model to understand what you're asking and the image embedding model to understand what's on the image. So lots of different things you can do. But one thing that I will focus on now, and partially because the whole world's now gone crazy about MCPs and agents, and you probably have heard these words all over the place. It's something that in LangChain4j is called AI services, and most people refer to as agents these days. And so I'll show you a very simple, don't confuse this with what the world out there talk about agents these days, but a very simple thing called in here AI service. So basically, we have the same scenario you've seen already many times. I want to learn to play a song on a piano. But this time, I'm going to use, again, Llama 3.2 through Llama. So this is my chat language model. And then I'm going to create an AI service, which is called librarian. And that service is going to use my chat language model. Right? And then I'm going to, instead of talking to the model like I did before, I'm going to talk to this agent or service, whatever you want to call it. And then it will talk to that agent on my behalf. Right? And so that's it. Now, the librarian thing, this is a LangChain4j specific way of defining it, is an interface. And so you just define an interface, and you use this system message annotation to tell the agent, to give the agent instructions. And in this case, it's a system message. It says, you're a librarian, respond with the names, brief summary, blah, 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 blah. You tell how the agent should behave. And that's it. if you go and run this code, you will see the same result we saw before, but as per instructions we provided to the agent, it basically just printed out 3 books instead of like, elaborative text, do this, do that. It basically says, those are the 3 books I know about. Now, I've been paying attention before, none of these books is in the list of books that we have, right? So if we were to build an AI agent that actually tells our potential customers what books we have in our bookstore, that's hardly useful, because this operates on training data, which contains whatever books it found when it was trained. So to actually make those agents accurate, we need something like that's been known for a while as RAG, Retrieval Augmented Generation. What basically this means is you have an accurate data somewhere. You retrieve that data based on the user's request, right? Based on whatever request is, you retrieve what's relevant to that request, and then pass that information to the LLM together with the query. Now, and then you instruct the LLM to respond using the data that you have provided. Now, the LLM is not hallucinating about things it doesn't know, but it just uses the data that you have provided. And if you work with proprietary data, company-specific data, something that the models are not trained on, that's the only way to actually do it. So it's a relatively simple way to do this with LangChain4j. So it's the same thing here. We this time using different model, Gamma 3, that's one from Google. It doesn't really matter, whatever runs on your Llama. You can try to, actually, when you build real applications, that's one thing you should be concerned about is which models works best for your use case. So don't just pick a model and assume it will be great. You would need to understand what those models are, how they work, and which serves your purpose. But this case, I use Gamma, not that it matters. It's a demo. I also have a line that connects to my Pinecone index, where I have my embeddings, which is where is the information about what actual books we have in our bookstore and what the library is about, what they are about. And then I have this thing, content retriever. Now, content retriever is as a LangChain4j concept that basically combines the entire retrieving process where we get the data from. And in this case, we say we get the data from an embedding store, which is that embedding store, and the data is embedded using that model. Now, the reason we need to give it the model is because it needs to know how to generate the query. Like, because if you use a different model to generate embeddings from the query, your vectors will not match. All different vectors will match. Right? So you need to know, when you query, you need to use the same embedding model. And we want 5 results. So this is our content retriever, basically. And then we have another similar concept that's called content injector. And content injector is basically the opposite. It basically tells, once I retrieve the data, which part of it I should pass down to the LLM. And we say, pass down the title. Because we already found the books that are relevant to our query. So the only thing we want is to pass the titles to the LLM so it can give us a nice formatted result. And that finally is the retrieval augmenter, which puts all these pieces together and say, here we're doing a RAG, and I want to use this content retriever and this content injector and build me that thing. And then I have the service that you saw already, which is using the chat model and is talking to the LLM on our behalf, right? And that's it, the answer we get from this. Now, the instructions for the agent here are a bit longer. This times we're explicitly telling the agent to not respond about things it doesn't know, to just limit the things to the data that we've provided, and whatnot. So let's run that and see the result. It should run fairly quick, and we should see that it responds in an LLM way. We currently have this book. Additionally, we have that book. And if you want to double check, those are all the books that we have in our store. Right? So what happened here is we found the books that based on the user request, we found the books in our store. We sent that to the LLM and told the LLM respond to that user with that information. And that's what ideally the user would get. So I'm not going to go into all of this. I can do like a whole day talk about LangChain4j and all kinds of other things. But this is just, as I said, scratching the surface. I hope it kind of gives you a mental model that I was looking for when I first started investigating this, to kind of put pieces together in your mind and understand what's where, how they work together, why it is this way and not the other way. And it opens the door for you to kind of go and explore way more, because there's like really a lot more to explore in that field. If by any chance you want to go deeper into how to train models and all the nuts and bolts and stuff in between, I highly recommend you to have a look at a deep Java library. Now, all these tools that I show you, they use deep Java library behind the scenes, right? So, but if you want to do more like low-level stuff, that's probably where you should start digging into it. And that's all I have for you for today. So I hope it was useful. I hope you learned something new. And I hope it's going to help you build the next beautiful and profitable AI. Thank you very much.